Hi viewers, this is Panikumar, Senior Lecturer in Chemistry. In the last video, we discussed about the chemical bonding and introduction, and we completed the Lewis dot structures. In the current video, we are going to discuss about valency bond theory. So here, before discussing valency bond theory, let's have a look on the basic fundamentals what we learned in the first video. What are they? What does it mean by a chemical bond? Nothing but the forces of attractions which hold either two or more than two atoms together is simply called as a chemical bond. So during the formation of chemical bond, what happens? The electrostatic forces of attractions which are present in between two different atoms are equal to the electrostatic forces of repulsions, and the electrostatic force of attractions and electrostatic forces of repulsions will exist at equilibrium in the case of a chemical bond. And next we discussed about different kinds of the chemical bonds. They are covalent bond, ionic bond, coordinate covalent bond, metallic bonding, and hydrogen bonding like we discussed. Next, in this video, we are going to discuss about the valency bond theory for the formation of a covalent bond. How a covalent bond is formed is explained by valency bond theory. So let us discuss about valency bond theory in this video. This valency bond theory is proposed by Hitler and London. These two different scientists proposed the valency bond theory. The valency bond theory is proposed by Hitler and London based on the Schrödinger wave equation. Based on Schrödinger wave equation, Hitler and London proposed the valency bond theory. And Pauling extended this valency bond theory to explain the structures of the molecules. Pauling explained this theory to explain the structures of the molecules. What are the postulates of this valency bond theory? So here what happens means during the formation of a covalent bond, so let me tell you what does it mean by a covalent bond. Covalent bond means nothing but the bond which is formed by mutual sharing of an electron pair is called as a covalent bond. Here during the formation of covalent bond, what happens? The two atoms involved in the bond formation contributes one electron each required for the bond formation. So during the formation of a covalent bond, what happens? The two atomic orbitals present in the valency shell of the atoms are overlapped. What happens? During the formation of a covalent bond, the atomic orbitals in the valency shell of the atoms, atoms overlaps one with another. What happens? The atomic orbitals in the valency shell of the two atoms involved in the bond formation overlaps one with another. So which kind of atomic orbitals will participate in the covalent bond formation? If in the valency shell, if you are having 4 atomic orbitals, is all the 4 atomic orbitals are involved in the bond formation or in the overlapping process? Means all the atomic orbitals are not involved in the overlapping process. The atomic orbitals which are half filled, only the half filled atomic orbitals are involved in the overlapping process. Only the half filled atomic orbitals are involved in the overlapping process. So here, as a result of overlapping, what happens means the electron density of the shared electron pair. That means the two electrons which are involved in the bond formation, that two electron density is mostly present along the internuclear axis. That is the third postulate. The electron density is mostly present. The electron density is mostly present along the internuclear axis. Okay, where the electron density is present, the electron density is present mostly along the internuclear axis. So due to the formation of a covalent bond, or during the overlapping process, what happens means simply we know that in atomic orbitals, the valency electron, that means if an unpaired electron is present in the valency orbital, either that might have either positive spin or negative spin. We cannot predict the spin of an unpaired electron. That might have a positive spin and or that might have a negative spin. But after the bond formation, what happens? The two electrons which are involved in the bond formation will acquire the opposite spins. If one is having positive and the second one is having negative, we cannot predict both the electrons are having positive spins or both the electrons are having negative spins. We cannot predict that. Okay, so both the positive spin electrons might be involved in the bond formation, both the negative spin electrons might be involved in the bond formation. One positive, one negative might be involved. Whatever it is, after the covalent bond formation, if one electron is having positive spin, automatically the second electron will acquire the opposite spin. Here, the strength of the covalent bond, next one, the strength of the covalent bond, covalent bond is directly proportional to the extent of overlapping. The strength of covalent bond is directly proportional to the extent of overlapping. The strength of covalent bond is directly proportional to the extent of overlapping. More the overlapping process, stronger will be the bond. Lesser the overlapping process, weak will be the bond. So the strength of the covalent bond is directly proportional to the extent of overlapping. And next, if I am saying here two electrons are involved in the covalent bond formation. So these two electrons which are involved in the covalent bond formation, let me say these two electrons are involved in the covalent bond formation between A and B. These two electrons which are present in the bonding orbital are attracted by both the bonded atoms. These are attracted by both the bonded atoms. Here one electron is contributed by A and one electron is contributed by B. One electron is contributed by A and one electron is contributed by B atom. So here what happens, let me say this is A atom and this is B atom. Here I am having an electron, here I am having another electron. So one is contributed by A and another one is contributed by B. So this electron contributed by A is attracted by A as well as it is attracted by B atom. And the electron contributed by B is attracted by B as well as attracted by A also. Here I told during the covalent bond formation, here the electrons will attain a opposite spin. That means here spin pairing takes place. Due to the spin pairing, what happens? Certain amount of energy is released during the overlapping process. That amount of energy which is released during the overlapping process and during the spin inversion or spin pairing is called as bond energy, that is called as bond energy. What does it mean by bond energy? The amount of energy that is released during the overlapping process and due to the spin inversion is called as the bond energy. And as I told in the beginning, which kind of the energies are involved here, which kind of forces are present here means here in the covalent molecule we are having two different types of forces: electrostatic forces of attractions and electrostatic forces of repulsions. How many kinds of forces are operating in a covalent molecule? Two kinds of the forces. What are they? Electrostatic forces of attractions and electrostatic forces of repulsions. Where the electrostatic forces of attractions are present, where electrostatic forces of repulsions are present. These electrostatic forces of attractions are present in between atom A, nucleus of atom A, and electron of atom B. Okay, the electrostatic force of attractions are present in between nucleus of atom A and electron of atom B. In the same way, nucleus of atom B and electron of atom A. In between these two, we are having electrostatic force of attractions. Due to these electrostatic forces of attractions, what happens? These atoms comes closer to one another. They comes closer to one another. After reaching certain distance, what happens means electrostatic forces of repulsion starts to be operating. Where the electrostatic force of repulsions are present means the electrostatic forces of repulsions are present in between. Listen carefully. The electrostatic forces of repulsions are present in between here the nucleus of both the atom A and atom B and electrons of atom A and atom B. In between these you are having electrostatic force of attractions, and here at the electrostatic force of attractions, here at chemical bond what happens? Electrostatic force of attractions are equal to the electrostatic forces of repulsions. Then the distance is called as the condition at which electrostatic force of attractions are equal to electrostatic force of repulsions is called as a chemical bond, or sorry, that is called as a bond length. If the distance, internuclear distance at which the electrostatic force of attractions are equal to the electrostatic force of repulsions is called as a bond length. Okay, that is called as bond length. If electrostatic force of attractions are equal to electrostatic force of repulsions, then the internuclear distance is called as a bond length. That is called as a bond length. Okay, let's have a quick review on the postulates of valency bond theory once. What happens? A covalent bond is formed by the overlapping of the atomic orbitals present in the valency shell of atoms. Only the half-filled atomic orbitals are involved in the process. Next, the electron density is mostly present along the internuclear axis. After the covalent bond formation, the spin inversion or spin pairing takes place. Next, strength of covalent bond is directly proportional to the extent of overlapping. And next, the bond pair of electrons are attracted by both the nucleus of atoms, and the bond energy means the amount of energy that is released during the overlapping process is called bond energy. These are the postulates of valency bond theory. Are you clear? So let us discuss about the concept of overlapping. During the formation of covalent bond, how atomic orbitals overlaps one with another, how many kinds of overlapping process are there. So here let us discuss about the concept of overlapping. Let us discuss about the concept of overlapping here. Totally, we are having three different kinds of the overlapping process. How many kinds of the overlapping process are there? Three different kinds of overlapping process are there. They are nothing but the first one is the positive overlapping, and the second one is the negative overlapping, and the third one is the zero overlapping. So here during the formation of covalent bond, we can observe three different kinds of the overlapping process. What are they? Positive overlapping, negative overlapping, and zero overlapping. What happens means, if an s orbital is considered, an s orbital is having only one lobe, and that is assigned with a positive sign. And if a p orbital is considered, a p orbital is having two different lobes, and one of the lobe is assigned with positive and one of the lobe is assigned with the negative. So here during the overlapping process, if overlapping orbitals are having same sign, if overlapping orbitals are having same sign, let me say here two s orbitals overlapped one with another, as an s orbital is having a same sign, that is called as a positive overlapping. And next here let me take two p orbitals like this laterally. Here the positive lobe of the p orbital overlaps with the positive lobe of the another p orbital, then that is also called as positive overlapping. And this is the lateral overlapping of the p orbitals or sideways overlapping. We will discuss which kind of bond is formed by the lateral overlapping or end-on-end overlapping. We will discuss in few seconds. Next, let me take if a negative overlap, positive overlap. So that is called as positive overlapping. In the same way, end-on-end overlapping might have been take place. If the positive lobe of a p orbital overlaps with the positive lobe by end-on-end process, then that is also called as positive overlapping. In the same way, if the negative lobe of a p orbital overlaps with the negative lobe of another p orbital, that also called as what we can say, that can also be called as positive overlap. And in the same way, if an s orbital overlaps with the positive lobe of the p orbital, that is also called as a positive overlapping. Okay, that is also called as a positive overlapping. This is what about the cases of positive overlap. And negative overlap. During the overlapping process, here opposite signs are overlapped. Here the same signs are overlapped one with another in all these cases. If opposite signs are overlapped, that is called as what we can say, negative overlap. That means if we cannot observe the negative overlap in between two different s orbital. If an s orbital with the positive lobe overlaps with the negative lobe of a p orbital, then that is called as negative overlap. That is called as a negative overlap. And in the same way, if the negative lobe of one p orbital overlaps with the positive lobe of another p orbital, then also that is called as a negative overlap. Then also it is called as a negative overlap. In the same way, in lateral overlapping also, if a positive lobe overlaps with the negative lobe, then that is also called as a negative overlapping process. And zero overlapping process. That means if an s orbital overlaps with a p orbital in the internuclear axis of the p orbital, like this, if the overlapping process takes place, that is called as a zero overlapping, that is called as a zero overlapping. In the same way, if p orbital along with the p orbital along the internuclear axis overlaps with the what we can say like this kind of p orbital, this is also called as a zero overlapping process. This is also called as zero overlapping process. So the zero overlapping process does not result in the formation of a covalent bond. Are you understand about the process of overlapping? Three different kinds, and this is the mode of overlapping of atomic orbitals. Are you clear? So if positive overlapping takes place, then what happens means due to the positive overlapping process, two different kinds of bonds are known to form. What are they means? Sigma bond and pi bond. Two different kinds of bonds will be formed due to positive overlapping process. What are they? One is the sigma bond and second one is the pi bond. One is the sigma bond and second one is the pi bond. What does it mean by a sigma bond? Means the bond which is formed by the end-on end overlapping of atomic orbitals. The bond which is formed by the end-on end overlapping of atomic orbitals is called as a sigma bond. And the bond which is formed by the lateral overlapping process, the bond which is formed by the lateral overlapping process, or we can say it as sideways overlapping, lateral overlapping or sideways overlapping process is simply called as a pi bond. Let us see how the overlapping process takes place in end-on end fashion. So here let me take an s orbital. If an s orbital overlaps with any of the p orbital, we know that we are having p orbitals in three Cartesian coordinates, px orbital, py orbital and pz orbital. Just like that, here if two different s orbitals overlaps one with another, that results in the formation of here a sigma bond. So here at the intersecting point you can find the bond pair of electrons. Here such a kind of bond which is formed by the end-on end overlapping of two s orbitals is called as a sigma ss bond. That is called as a sigma ss bond. Let us have an example for this. Here the best example for the molecule which is having a sigma ss bond is a hydrogen molecule. It is consisting of two different hydrogen atoms, and each hydrogen atom is having we can say 1s1 electron configuration. So here what happens, the 1s orbital of one hydrogen atom overlaps with the 1s orbital of another hydrogen atom to form a hydrogen molecule. The 1s orbital of one hydrogen atom overlaps with the 1s orbital of another hydrogen atom to form a sigma ss bond over here. So here what we can say, before the bond formation, the unpaired electron, one and only unpaired electron which is present in the 1s orbital, that might have either plus half spin or minus half spin. We cannot predict the spin of electron. But after the formation of this covalent bond, after the overlapping process, one electron is having plus half spin and another electron is having minus half spin. In the same way, this is first process in the formation of a sigma bond. Let me take the second process. Here an s orbital with an unpaired electron might overlap with the p orbital of another atom which is having unpaired electron. Then also what we can find a sigma bond. Here positive overlap takes place. Okay, here as a sigma bond is formed in between s orbital and p orbital, that is called as sigma sp bonding. That is called as sigma sp bonding. Let me see the molecule having sigma sp bond. That is nothing but an HCl molecule. It is having two different atoms. What are they? One is the hydrogen, second one is the chlorine. Let us take the valency shell electronic configuration for the chlorine. That is NS2 NP5. In postulates I told, let us remember once. Here in NP orbital you are having, in orbital diagram method, let us write the electronic configuration of p orbital. NS2 NP5. So 2 electrons are present in the NS orbital and 5 electrons are present in the NP orbital. So here in the valency shell of the chlorine, altogether you are having 4 atomic orbitals. All these 4 atomic orbitals does not involve in the bond formation. They does not involve in the bond formation. Only the atomic orbital which is having unpaired electron involves in the bond formation. The atomic orbital which is having an unpaired electron will involve in the bond formation. So what happens? The 1s orbital of the hydrogen atom overlaps with the p orbital of the chlorine which is having an unpaired electron to form a HCl molecule. And third kind of the sigma bond we can expect, that is in between two p orbitals. So here the p orbital of one atom overlaps with the p orbital of another atom to form a sigma pp bond. A sigma pp bond is formed. So this kind is observed in Cl2 molecule. See, here already we are having, here the p orbital which is having unpaired electron overlaps with the p orbital of another atom which is having unpaired electron to form the chlorine molecule. This is what about the sigma bond formation. Next, pi bond formation. What does it mean by a pi bond? The bond which is formed by the lateral overlapping of atomic orbitals is called as a pi bond. Here let us take mostly a pi bond is formed in between two p orbitals, and here we can say in between d orbital and p orbital, or in between two d orbitals. If two p orbitals overlaps one with another laterally or sideways, that results in the formation of a pi bond. If a pi bond is formed due to the lateral overlapping of two p orbitals, that is called as pi pp bond. That is called as pi pp bond. So we will see the examples for the formation of pi bonds at the end of this video. And the next, if a p orbital overlaps with the d orbital, if a p orbital overlaps with the d orbital, then the bond formation is called a pi bond will be formed, and the so formed bond is called as a pi d pi bond, like this. So this is called as pi p d bond or pi d p bond. That is called as pi d p bond or pi p d bond. If two d orbitals are involved in the lateral overlapping process, if two d orbitals are involved in the lateral overlapping process, then what happens? Nothing but that also results in the formation of another pi bond. That is called as, that pi bond is called as a pi dd bond. That is called as a pi dd bond. Like this, due to the positive overlapping process, we can expect two different kinds of the bonds. Here you have to remember 3 points. These are the 3 major points we have to remember. Number 1, always a pi bond is formed after the formation of sigma bond. If you want to make a pi bond, if one sigma bond is formed, then only a pi bond is formed. That is first point you have to remember. What is that? Pi bond is formed after the formation of a sigma bond. This is point number 1. You have to remember, the most important point. And next, a sigma bond is always a stronger bond than pi bond. Sigma bond is always a stronger bond than pi bond. Next, here to form a bond, the orbitals should be in the same axis. If either sigma bond has to be formed or pi bond has to be formed in between two different atomic orbitals, then if the two atomic orbitals which are involved in the pi bond or sigma bond should be in the same axis. For example, if you want to form a sigma bond in between p orbital and s orbital, these two orbitals should be in the same axis. Or a sigma bond is formed in between either px orbital or px orbital, or that might be py or py, or pz or pz, because we cannot say here either px orbital will form a sigma bond, py orbital will form a sigma bond, or pz orbital is forms a sigma bond. So based on the literature, in the older literature, as per old literature, px orbital is known to present along the internuclear axis, that forms a sigma bond, and then py and the pz orbitals will form pi bonds. But in the modern literature, it was described that pz orbital is present along the internuclear axis, so that forms a sigma bond. Then px and the py orbitals will form a pi bond. We cannot define ever which p orbital will form a sigma bond, because x, y, z Cartesian coordinates are the imaginary axis. So as they are imaginary axis, if I assume x is along the internuclear axis, that forms sigma bond. If y is assumed along the internuclear axis, that forms sigma bond. Z, that forms sigma bond. So as x, y, z planes are the imaginary planes, we cannot say this alone forms a sigma bond. In the same way, if you want to form a pi bond using py orbital, between py and py only pi bond will be formed. A pi bond is never formed in between px orbital versus py orbital, or py orbital versus pz orbital, or px orbital versus pz orbital. So because these two orbitals are not in the same plane, so a bond is never formed. Either if you want to make or a sigma bond or pi bond, the atomic orbitals should present in the same axis. Did you understand my point? So now let us discuss about the differences between sigma bond and pi bond. What are the differences between a sigma bond and pi bond? Okay, now here already I told the first difference between sigma bond and pi bond is nothing but mode of overlapping. A sigma bond is always formed by the end-on-end overlapping process. Sigma bond is always formed by the end-on-end overlapping process. And next, a pi bond is always formed by the lateral overlapping process or sideways overlapping process. Okay, so pi bond is formed by the lateral overlapping process or sideways overlapping process. Next, second difference is a sigma bond is always called as a localized bond. A sigma bond is always called as a localized bond, and a pi bond is always called as a delocalized bond. It is always called as a delocalized bond. Why sigma bond is called as a localized bond and why pi bond is called as a delocalized bond means, after the formation of a sigma bond, let me take an example, best example, using p orbital, sigma bond formation using p orbital. So after the formation of sigma bond using two p orbitals, the electron cloud is present only in between the two nucleus. But in the pi bond, what happens? Simply the electrons which are involved will revolve around the nucleus. Some of the times that might be present on the top lobes, some of the times they are present in the bottom lobes. So that is called as a delocalized bond. And already I told, based on the strength, sigma bond is a strong bond and a pi bond is a weak bond. Sigma bond is called as a strong bond, it is a strong bond, and a pi bond is a weak bond. And next, the compounds which are having sigma bond are called as saturated molecules. If all sigma bonds are present, all the bonds that are involved in the molecule formation are sigma bonds only, then they are called as saturated molecules. If any pi bond is present in the molecule, that is called as an unsaturated molecule. That is called as an unsaturated molecule. And a sigma bond, already I told, the most important point you have to remember, a sigma bond, after the formation of sigma bond only a pi bond is formed. That means a sigma bond can exist independently. A sigma bond can exist independently, whereas a pi bond cannot exist independently. A pi bond cannot exist independently, whereas a sigma bond can exist independently. Next one, we can say the sigma bond decides the shape of the molecule. A sigma bond decides the shape of the molecule, and a pi bond does not influences the shape. It does not influences the shape of the molecule. And next, here the compounds with the sigma bond are less reactive in nature. The compounds with the sigma bonds are less reactive in nature, and the compounds with the pi bond are more reactive in nature. Compounds with the pi bonds are more reactive in nature. And next, if we observe the overlapping process, the overlapping during the formation of sigma bond, the overlapping takes place along the internuclear axis. The overlapping of atomic orbitals takes place along the internuclear axis. That is the imaginary plane which passes through the nucleus. And next, here in the pi bond, what happens? The overlapping takes place above and below the internuclear axis. During the formation of the pi bond, what happens? The overlapping takes place above and below the internuclear axis. So here a sigma bond is formed by the SS overlapping or PP overlapping, or it might be formed by the SP overlapping. But a pi bond is mostly formed by the PP overlapping only. These are the major differences between sigma bond and pi bond. Are you clear, students? So here we have to remember few points. That is, bond strength is directly proportional to two different factors. Number one is extent of overlapping. The bond strength is directly proportional to extent of overlapping process. Second one is the bond strength is directly proportional to number of bonds present between the atoms. The number of bonds present between the atoms. Here there is an exception you have to remember, that is extent of overlapping. Based on extent of overlapping, we are having an exception. That is, if the over 1s orbital and 2s orbitals are considered. Which orbitals? 1s orbital and 2s orbitals are considered over here. What happens means extent of overlapping is more for 2s orbital. Extent of overlapping is more for 2s orbital. But the bond which is formed by the overlapping of 1s orbital will be a strong bond. The bond which is formed by the overlapping of 1s orbital will be a strong bond. So the reason for this is due to the size of these atomic orbitals. Due to the size of atomic orbitals, the bond which is formed by the overlapping of two 1s orbital will be strong, and the extent of overlapping will be more for the overlapping of two 2s orbitals. And if you observe the extent of overlapping order, the extent of overlapping order is more for two p orbitals. Sigma pp bond is having more extent of overlapping than sigma sp overlapping, than sigma ss overlapping, than a pi bond. Okay, this is the order of the extent of overlapping. In the same way, strength of the bond is more for the compounds which are having a triple bond between two carbon atoms, and than the compounds having a double bond between two carbon atoms, than the compounds having a single bond between two carbon atoms. Are you clear, students? You have to remember these points. These are most important for you. So let us see the formation of few molecules through the valency bond theory. Let us see the formation of oxygen molecule. So this oxygen molecule is formed by the overlapping of atomic orbitals present in two oxygen atoms. Let us see the electronic configuration of oxygen atom. So we know that oxygen electronic configuration is 1s2, 2s2, 2p4, and as I told, as per the valency bond theory, only the atomic orbitals present in the valency shell are involved in the bond formation. So 2s and 2p orbitals might have been involved in the bond formation. So let me write the electronic configuration in the orbital diagram method, then we can understand better. Okay, so this is the electronic configuration of oxygen atom in the orbital diagram method. So let me say this is a px orbital, this is a py orbital, and this is pz orbital. So here this is 2s orbital. As 2s orbital and px orbitals are having completely paired up electrons, they does not involve in the bond formation. Only the half-filled atomic orbitals are involved in the bond formation. So let me imagine the pz orbital is present along the internuclear axis. So what happens? The pz orbital of one oxygen atom overlaps with the pz orbital of another oxygen atom to form a oxygen-oxygen sigma bond. Oxygen-oxygen sigma bond. And then here I am having a py orbital. Let it be py orbital. This is also having an unpaired electron. So the py orbital of one oxygen atom overlaps with the py orbital of another oxygen atom to form a pi bond. So a pi bond is formed, and then after that you are having p orbital also. So this p orbital is having a paired electron, right? So what happens? Each oxygen atom and a paired up electron is present in the 2s orbital. So in oxygen molecule, here the two oxygen atoms are having two lone pairs each. So here we can have one important question and most interesting point here. Based on the observation, while we discuss about the magnetic character or magnetic nature of a compound, we will say if it is having unpaired electron, that is having paramagnetic nature, and if it is having completely paired up electrons, that is said to be having a diamagnetic nature, right? Here we cannot find any unpaired electron in the oxygen molecule. So 4 lone pairs and 2 bond pairs are there. But surprisingly, the oxygen atom is paramagnetic in nature. The paramagnetic nature of the oxygen atom is explained by molecular orbital theory. What we can explain, it will be explained in the molecular orbital theory at the end of this chapter. Next, let us see the formation of N2 molecule. It is having 2 nitrogen atoms and the electronic configuration will be 1s2, 2s2, 2p3, and in orbital diagram method we can write like this. So 2s2 and 3 unpaired electrons are present in the nitrogen atom. So it involves in the formation of 3 bonds. Let me say the px orbital, py orbital and pz orbital. If pz orbital is present along the internuclear axis, a sigma bond is formed by the overlapping of 2 pz orbitals. So in between 2 nitrogen atoms, 1 sigma bond is present, and we are having 2 more orbitals px and py which are having unpaired electrons. So in between these two, what happens, we can expect a pi bond. So totally we are having 2 pi bonds in the nitrogen atom and 1 sigma bond. It is having 1 sigma bond and 2 pi bonds. As you are having a lone pair in 2s orbital in the valency shell, we can have 1 lone pair of electron in each of the, what we can say, nitrogen atoms. And let us explain about the water molecule formation. Here the central atom is oxygen, and the oxygen electronic configuration in orbital diagram method we can write like this. Already I told you that it is having 2 unpaired electrons, and the 2 unpaired electrons overlaps with the s orbital of the hydrogen atom to form 2 sigma bonds, and it is having 2 lone pairs of electrons. And the last example of the day, that is methane molecule, and here the central atom is the carbon atom. Its electronic configuration is 1s2, 2s2, 2p2, and in orbital diagram method we can write like this. It is having only 2 unpaired electrons, but in methane molecule we are having 4 hydrogen atoms. So what we have to take, this is the ground state electronic configuration. We have to take the first excited state electronic configuration. Then the electron in the 2s orbital is excited to the 2p orbital. Then in first excited state we can find 4 unpaired electron. We can find how many unpaired electrons? 4 unpaired electrons. And these 4 unpaired electrons overlaps with the s orbital of hydrogen atom to form 4 sigma bonds. Right. Here what happens means, as per the valency bond theory, 1 sigma bond is formed by the overlapping of s orbital and s orbital, and 3 sigma bonds are formed by the overlapping of s orbital and p orbital. So the methane molecule should have 2 different kinds of the bond lengths, but surprisingly it is having only 1 kind of bond length. So the uniform bond length in the methane molecule is explained in tomorrow's topic, so don't miss it. Very good. Thank you, friends.